Hello, students. Mr. Murphy here. So today's lesson 3, we're going to know that positive square roots and the cube root exist for all positive numbers, and both a square root and a number of a cube root uh, are unique. So square root of a number and the cube root of a number are unique. And then we're going to solve simple equations that require you to find a square root or a cube root. Okay. So that's our objective. Let's see what's going on. This is going to be kind of long and dense to start with, and then I'm going to recap everything. So follow along as best you can, and then pay real close attention on the recap. All right. So let's start with something really simple. Think of a number that is both equal to 3 and larger than 3 at the same time. Think about that for a second. Can you think of a number that is both equal to and larger than 3 at the same time? Okay. I can't think of anything because 4 is bigger than 3, but is not equal to 3. And I can change 3 around. I can say 3 over 1 is equal to 3, but it's not larger than 3. I can even say 9 over 3 is equal to 3, but it's not larger than 3. I could say 1/3 times 9 equals 3, but it's not larger than 3. So I can't think of a number that is both 3 and bigger than 3 at the same time. So in math, they don't like to say specifics because then you got to go, okay, how about 4? Okay, how about 5? So you've got to go on and prove every single one, or you can prove the general. And one way we can prove things is to prove the opposite is wrong. So let's assume there is a positive rational number that is equal to, so I have x is a positive rational number and it's equal to y, and at the same time, x is also larger than y. Okay, so notice we have some limitations. It's just positive rational numbers, and it's both equal to and greater than the number. So that's what we're proving. If we have negatives or fractions, or well, fractions will work, but if we have negatives and irrational numbers or anything else like that, it may not be true. But we're going to figure out for positive if it's true or not. So we can start with this. Let's say this is my proof. So I didn't read it in a book, so I don't know if this is good or not. So we'll take a look. Let's say a number on a number line, right? So we've got, if you put a number on a number line, there's only one spot for that number. And on a number line, when numbers get bigger, they go on the right. So if x equals y, then they have to be on the same spot on the number line. But if x is bigger than y, then x is to the right on the number line. So here's my number line on the bottom. If x is bigger than y, it's to the right of y. It's not on top of y. So x can't be in two places at the same time. So I cannot have a number, any number, x, that is both equal to y and greater than y. So I proved that, I assumed that there was a number, and then I proved, well, that's impossible. So now I can say, basically, if x is a number, a positive number, then either x equals y, x is greater than y, or x is less than y. Okay, that's a trichotomy, which means you just break something into three parts. All numbers are either equal to, greater than, or less than another number. Okay, so we're going to move on to squares with this. So now we know numbers are either equal to, greater than, or less than. So they're unique, right? All numbers are unique. They're either the same number, or they're bigger than the other number, or smaller than the other number. So now I'm going to start with two other numbers, c and d. They're both positive numbers. If I square c, it's going to be less than the square of d. If they start to be bigger than each other, then when I square them, they're still going to be bigger than each other. But if c is less than d, c is not equal, c squared is not equal to d squared. And if c is less than d, then c squared cannot be bigger than d squared. So looking back at that last one where a number is either equal to, greater than, or less than. This holds true for squares too. If a number is less than, it's going to stay less than. If the number is equal to, it's going to stay equal to. If the number is greater than, it's going to stay greater than, right? And now that we've shown that this is a property and this is true, we can look at examples. So let's say I have two numbers C and D. If I square them, so 2 is less than 3, then 2 squared is less than 3 squared. And I know that's true because 4 is less than 9. If 2 is less than 3, then 2 cannot be equal to 2 squared cannot be equal to 3 squared because 4 does not equal 9. And then again, 2 is less than 3, then 2 squared is not greater than 3 squared because 4 is not greater than 9, or 4 is less than 9. So what holds true for regular positive numbers also holds true for the squares of those regular positive numbers. Okay, so going on to something else. Why do we care about this stuff, right? So this is a lot of dense stuff that you don't understand. Here's why we care. And it's almost always the backwards of the way I wrote the rule, right? If a number is bigger, then when you square it, it will still be bigger. If I have a number and I want to find the square root, then a bigger number will have a bigger square and a smaller number will have a smaller square. And I know you're going, who cares, Mr. Murphy? It's obvious, and who really cares? Well, here's why it really matters, right? If I have it, so I know all of my doubles. I know 7 times 7 is 49. So the square root of 49 is 7. And I know 6 times 6 is 36. And the square root of 36 is 6. So if I have a number between 36 and 49, like the number 40, then the square root of 40 has to be between 6 and 7, right? So if square root of 49 is 7 and square root of 36 is 6, then the square root of 40 must be between 6 and 7. And I know that sounds obvious, and a lot of you guys are like, I did that yesterday in homework, Mr. Murphy. That's all right. Math is sometimes about doing stuff, but it's also about defining specifically with very great precision exactly what stuff is. And that's what we're doing here. But we can extend this, right? So instead of a square root, this is called a cube root. That means instead of finding a number times itself that equals 125, I'm looking for a number times a number times a number. So the number 3 times, not 3 times the number, but the number multiplied 3 times. So 5 times 5 times 5 is 125. The cube root of 125 is 5. And I can change this number. I can make it a 4 or a 5 or a 10 or 100. And that would say the fifth root of this number equals the number that times itself, times itself, times itself, times itself, times itself, equals whatever's in there. So we're just going to worry about cubes and squares for the moment. So if 125, the cube root of 125 is 5, and the cube root of 216 is 6, then the cube root of some number in between 125 and 216 is a number between 5 and 6. So I can use this to start estimating stuff. I can figure out triples, right? I can just guess and check stuff to figure out triples. It takes a little work, but it doesn't take too long. So if I'm got a number like 200 and somebody says, what's the cube root of 200? Then I just start multiplying the number 3 times, right? I'm going to go 5 times 5 is 125. That's less than 200. 6 times 6 times 6 is 216. That's bigger than 200. So the cube root of 200 must be something between 5 and 6. And I can even go farther and say 200 is closer to 216 than it is to 125. So maybe it's something like 5.8. I have no idea. Do it on your calculator. Do 5.8 times 5.8 times 5.8. Is it close to 200? Okay. You can get closer, but that's going to be an irrational number, right? The cube root of 125 is a rational number because it comes out to a nice whole number. The cube root of 200 is going to be an irrational number because it's going to end up being a decimal that goes on forever and ever and ever and never ends. Okay? Right. Mathematicians might even go on and say, hey, if I have the nth root of a number equals a, and the nth root of another number equals b, then the nth root of the third number that is between x and y must be between a and b. So I can extend this on to anything if I want. Right? One last easy proof for you to see, right? So you may not have understood all of the words that I was making, but this you may get, right? So if x is greater than y, then x squared is greater than y squared. So if I take a line, x is the length of this line, y is the length of this line, then when I square it, x becomes a square this big, and y becomes a square this big. And you can see the square of x is bigger than the square of y. So I can say for all positive numbers, when x is bigger than y, then x squared is bigger than y squared. And I can say that for all positive numbers because I just picked random lengths. And it works for any random length. It works for any random number. Okay. All right. So here's that recap. So take a little break if you need to. Come on back. Get a pencil and paper. Take a quick note. So we said if I have a number x and y, then x is either equal to y, bigger than y, or smaller than y. And if I have a number that is bigger or smaller than another number, then the square will be bigger or smaller or equal to another number. And this is useful because I can find the approximate value of a square root or a cube root or anything by finding which two perfect squares it's in between. All right, let's do a little practice on our calculator. So here's a simple equation. If x squared equals 25, solve for x. First thing I do is find the square root of both sides. So the square root of x squared is just x. Square root of 25 is 5. On the calculator, here's the calculators we usually have in school. I type in 25 and I press the square root key, which is this one here. Cube roots kind of work the same way. So if x cubed equals 125, find the cube root of both sides. So I do cube root of x cubed is x, cube root of 125 is 5. And I can do cube roots with this. See this green above here? So if I remember correctly, you would press 3, then you press the second button, then you press this, and then you type in 125 and hit equals, and it should give you 5. It may be a little different, and some calculators are different, right? So your simple equations, find the square roots, right? And I could do this with a calculator. If this was a different number, if this was like 30, then I'd say the square root of x squared is x. The square root of 30 is a number bigger than 5, smaller than 6, or a number about 5.5. Or I could put it in the calculator and type the square root key, and then I type 30 and hit enter, and it would give me a different number. Okay? All right, that is everything. I hope you got through all of that. I know it was a lot, but We'll see you soon.